Looking at lesson 4.3, linear regression. Definition: linear regression. Taking bivariate data and by bivariate I mean two variable, that is xy data, plotted points. In creating a model, and by model I mean both a line and an equation. To predict y given some x value. And again, this x and y, they're arbitrary. It could be whatever the variables. Take some input value and predict some corresponding output. How do we perform a linear regression with technology? Well, first, the kind of regression that we're going to perform is called an LSRL, and this stands for least squared regression line. Least squares regression line. It's a line that essentially averages our points. It reduces the distance between each one of those points and this line that is drawn to be the least possible distance. You can make this with a graphing calculator. And if you have a TI-84, you may be familiar with the StatCalc4 process. If you're not, I will make a separate video that shows how you can use your TI-84 to produce this. You can do it in Excel. If you put some bivariate data in Excel, Excel will draw a nice trend line for you automatically. And then I'm going to show now an online version using something we've already seen, MetaCalculator. Okay. Well, like we've done before, just search graphing calculator. And you'll notice the fourth hit down here that says metacalculator.com. We've already used that before. Graphing calculator, metacalculator. Previously, we've used this graphing calculator feature. Now we're going to use statistics calculator. Performing a linear regression is a common thing in statistics. Alright, now what you'll see here is some tabs. One says statistics calculator, one says basic statistics, and then you see it says regression analysis. Click the tab that says regression analysis. Now it gives us some columns. It says X and then F. Well, this is their output variable again. It can be anything. We typically use Y. Here they're using F. But what you see is we're ready for ordered pairs, for bivariate data. This is your input column. This is your output. Alright, I'm going to look at a particular problem. Okay. Our problem here says life expectancy in the United States has been rising since the 19th century. The table shows the U.S. life expectancy in selected years. If you were born in 1950, you were expected to live 68.2 years all the way to 2000. you would be expected to live 77 years. If we graphed this, we would see that as x increases, y increases. All right, and you should always graph, but here I'm talking about making the regression using this calculator. So I'm going to enter this data in my table. 1950 is an x value, and the corresponding y value is 68.2. 1960 pairs with 69.7. 1970 pairs with 70.8. 1980 with 73.7. 1990 with 75.4. 2000 with 77. All right, once you have your data in there, you simply hit analyze. And it gives you the regression equation. Y is equal to negative 288.6762 plus 0.1829x. That is our equation. This equation, y equals, I'm going to do a little rounding here, negative 289 plus, let's go with 0.18x. All right. This x is our x here, the year. So this y, and typically when we talk about our prediction equation, we'll use y hat. It's predicted y, refers to our life expectancy. So you could take some year and substitute it in here, and it will predict your life expectancy. This model is the LSRL, the least squared regression line. It is effective for taking some year x, substituting it in, and predicting some y. Now, of note, we should only use values, x values that we have in our domain. That is, it's really only meant to predict from 1950 to 2000. Using it beyond that, it's called extrapolation, and our model may not be effective for those values. How do we perform regression without a calculator? All right, well, if we have some points and they're scattered about on a graph and we want to come up with an equation, then we will first draw a line by hand that fits the data well. And then we will pick 2 points on that line. That's the key, on the line, not 2 points from our data. Using 2 points that are on that line that we just drew, we will write an equation. All right, let us look at an example of that. This is from this is from your XYZ homework. Okay. We're given a few points here, and it asks us to come up with an equation of the line and then select from these. Well, you could indeed enter these points in the website that we just came from, and it would give you the equation of the line. We absolutely could. But sometimes it's going to be easier just to come in and draw a line that best fits it. And I can see if I drew a line somewhere like this, it's going to fit my data pretty well. All right. So I'm thinking right through there is fitting my data pretty well. Now, I don't know if this line is exactly right, but you can see that it's pretty decent. Okay. Notice I sort of I didn't even though these arrows are extending forever, we should only consider it for data that we have values for. Okay. First of all, the line is moving up from left to right. The slope's positive. As our years are increasing over here, whatever it is we're counting on this side is increasing as well. Since the slope is positive, it couldn't be this first one because it has a negative slope, nor could it be this last one. Okay. Of these last two, they're pretty similar. This one, the slope is much greater. They flip the slopes in the y-intercepts. And looking at my line, it looks like I might have more of a slope of, a y-intercept of 2.6. But how I'm going to find this now is simply take 2 points off my line. This point I picked because it's real close to that intersection of 10, 30. 10 pairs with 30. All right. And then here's another one. That appears to be 20 pairs with 60. It's a little bit less than, let's say, 20 pairs with 58. Okay. Now I can use these 2 points to find the equation of a line. Well, you may remember from the last section we learned about point slope form. Point slope form. The point slope form said that we could get the equation by y minus y1 is equal to our slope times x minus x1, where this x1 and y1 is either one of our points. I'm going to use my 10, 30 here. So y minus 30 equals, now I need my slope. Well, remember how we found slope? Slope was a change in y divided by a change in x. Alright, so my change in y, I would subtract my y's, 58 minus 30 in this case. And my change in x is 20 minus 10. 58 minus 30 is 28. 20 minus 10 is 10, so this is 2.8. That's my slope. So in place of m is 2.8. And I can already see that's closest to this one. That has a slope of 2.6. X minus x1. I used 30 for my y, so I must use 10 there. Okay, so y minus 30 equals 2.8 times x is 2.8x. 2.8 times minus 10 is a minus 28. Adding 30 to both sides. Those cancel, leaving y equals 2.8x. And this will be plus 2. Alright, so I can see that I've missed my y-intercept a little bit, but I believe that the best answer here is going to be h. Okay. Now again, these equations are very close. Perhaps the better way to do this one will be to use the technology, but I'm feeling pretty good about this this 4.7 plus 2.6 because of the slope being so close there. All right. A small change would have really affected my y-intercept here, but the slope, is probably a better indicator in this case. you should be able to handle the problems on 4.3 with this information.